All right, so now that we know how unit step functions behave, and we know what it means when we say we're doing some function times a unit step function. So like right here, this f of t times u of t minus a, it means I would have 0 all the way up until a, and then at a, starting at a on, I've got this function showing up. Okay, so now let's see how Laplace transforms behave with some function times a unit step function. According to this rule here, we're going to have e to the negative as times the Laplace transform of f of t plus a. So what that means, I think it'll be clearer if we see it within a specific example. Here in this example, our f of t is this t squared, right? So f of t is t squared. But to use this formula to find this Laplace transform of f of t times u of t minus a, I need to know what f of t plus a is, right? So here's f of t, but what's f of t plus a? Well, in this case, what's a? A is 2. All right, so I need to do f of t plus 2. F of t plus 2 is t plus 2 squared. So then to do this Laplace transform, the answer, according to this formula, is going to be e to the negative as, so it's e to the negative 2s, times the Laplace transform of f of t plus 2, which is t plus 2 squared in this case. The Laplace transform of t plus 2 squared. So we've taken this Laplace transform of a function times a unit step function and turned it into the Laplace transform of something we know how to handle using our table of Laplace transforms. And then we've got this extra e to the negative 2s that shows up. To do our Laplace transform now, we need to first multiply this out. If you look at your table of Laplace transforms, this does not show up. But if I multiply this out and rewrite this as t squared plus 4t plus 4, I do know the Laplace transform of each of those straight from our table. All right, so this is e to the negative 2s times the Laplace transform of t squared plus 4t plus 4. So I have e to the negative 2s. And then we do the Laplace transform of each of these just straight from our table, 7.1 on page 356. The Laplace transform of t squared, that's t to the n, where n is 2. So I've got 2 factorial, which is just 2, divided by s raised to the 2 plus 1 power, so that would be s cubed. Plus 4 times the Laplace transform of t. The Laplace transform of t to the first power is 1 factorial over s squared. So I would have 4 over s squared. The Laplace transform of 4 would just be 4 over s. All right, so the Laplace transform of some function times a unit step function gives you an exponential times the Laplace transform of a shifted function, f of t plus a. All right, now This is the Laplace transform. We'll also want to go backwards. If I have to do the inverse Laplace transform of something that looks like this, or I've got an exponential times some things that I know how to work with, then we can do that as well. And we should expect that our final answer should involve a unit step function if we're working in the opposite direction. All right, so let me show you what this looks like with inverse Laplace transforms. So here's our rule for inverse Laplace transforms. Suppose we know that the inverse Laplace transform of capital F of S is f of t. Okay, then the inverse Laplace transform of that same capital F of S just being multiplied by this exponential function is equal to this shifted function times the unit step function f of t minus a times u of t minus a. All right, so again, let's just use this property to find this inverse Laplace transform. In this case, our e to the negative as, in this case, a is 4. Our capital F of S is this piece right here. And we know the inverse Laplace transform of that, right? So coming back to this original statement here, what is the inverse Laplace transform of capital F of S in this case? 1 over s minus 2 squared plus 1. What is the inverse Laplace transform of that? Again, look in your table of Laplace transforms, and you see that this fits that e to the at sine bt case. So here b is 1 and a is 2. So it have e to the 2t times sine of t. All right, so we know the inverse Laplace transform of this, but we want the inverse Laplace transform of this times this exponential function. So then using this rule, the inverse Laplace transform of something we know how to handle times an exponential function is going to be f of t minus a times u of t minus a. Where a is 4, f of t minus 4 times u of t minus 4. But what is f of t minus 4? Well, this thing right here is f of t, right? It's the inverse Laplace transform of our capital F. It's f of t. So this thing right here is f of t. So then what is f of t plus f of t minus 4? F of t minus 4 is e to the 2 times t minus 4 sine of t minus 4. All right, so we get e to the 2 times t minus 4 sine of t minus 4 times u of t minus 4. All right, so those two properties will be pretty useful to you in your homework for this section. We'll be solving differential equations, so you'll take the Laplace transform of both sides of the differential equation, and then do a little bit of algebra, and then you'll need to do the inverse Laplace transform. And so both of those will involve unit step functions. You'll do the Laplace transform of some function times a unit step function, and then do solve your equation, and then you'll need to undo, so you'll do the inverse Laplace transform. So then your final answer will also involve a unit step function like we have here. All right, so that's all I want to do with this video. In the next video, maybe I'll show you an example of how to use this to solve a differential equation.